Okay, good morning. I am glad to see that at least some people survived the party yesterday. Okay, if you remember, yesterday we started to discuss some equations about the arithmetic structure, I would say, of some structure of some quantities associated with elliptic curves. In particular, I mentioned that primality is kind of out of reach because even we don't have a proper background from analytic number theory. But for somewhat relaxed questions about elliptic curve cardinalities with large and small prime divisors, you really have a chance to do something. It has not been done, but at least there is a chance to say something interesting. For example, there is a result of Green-Harman, which says that the intervals of the length about square root of q contain a positive proportion of integers with a large prime divisor. So it gives you a chance. Certainly, you can ask a question about a typical behavior of the number of prime divisors. And here, under the GRH, we have a result which actually tells us everything what we wish to know, and namely the result which says that if you have a non-CM curve, then under the GRH, the typical number of prime divisors is close to what it should be for a random integer. Namely, it's double log p. And it's even the mean square. It's not just the mean, the average value. It's the average deviation, which is small. So it's a very nice result. And you will prove the same result for CM curves unconditionally, as it usually happens in equations of this type. Well, another way to approximate kind of primality is to limit the number of prime divisors. We don't care about the size, but we want the number of prime divisors to be small. And Chantal actually explained it yesterday how to approach, and that actually here I didn't specify the constant. And yesterday I learned, to my surprise, that even what you get for the constant is very close to what it should be. So the constant is actually very close to the expected values, which is very nice. And here's the summary of what we know. We know that for non-CM curves, we can push the number of prime divisors counted with multiplicities up to 8. And for CM curves, it's at most 2. Well, you can kind of modify this equation a little bit and ask the same equation, the equation of primality, not for the number of points, but for the trace. And again, you can modify this equation, you can relax it, you can massage it in different forms, ask what happens individually, on average, what about small values of omega, what about large prime divisors of this quantity. There's a whole spectrum of equations you can address. Well, you can ask, what's the motivation behind this? There is a clear motivation behind equations of primality. It comes from cryptography. Right? This equation doesn't seem directly linked to anything, and you can ask what's the motivation. And first of all, I want to quote Drew, something which he mentioned a few evenings ago. If you need a motivation, you are not a mathematician. And there is one more kind of reason to look at this equation. And let me explain why I think this equation still deserves some study. And actually, there is a motivation. If you want to talk about the primality of the number of points, it's a natural equation. But from kind of Chebotarev point of view, it's not a natural equation. To control the behavior of this guy in arithmetic progressions, so that's what we need for sieving, you have to do two things simultaneously. You have to control p in arithmetic progression, and essentially the basic form of Chebotarev theorem, the Dirichlet theorem about primes in arithmetic progressions. And you also control AP. So you kind of apply Chebotarev to two different quantities, which it still can do. But if you talk about primality of just the Frobenius trace, you don't have to worry about p. It's just kind of single Chebotarev. So hopefully the error term will go down. Hopefully we'll get better results. Don't think anybody tried to look into this. Maybe I'm too optimistic. Maybe this won't happen. It still deserves some study. Okay. Now, and one more issue about arithmetic structures of quantities associated to elliptic curves is the question about CM discriminants. You know that if you're interested in CM fields of curves over finite fields, you should look at this quantity. But this is not the discriminant. It's a square part of this quantity, which is important to us. And typically, almost all numbers have a tiny square divisor. I'm not saying that almost all of them are square free. What's really true that almost all of them are almost square free, meaning they have a tiny square divisor. But it's a typical behavior of integers. We don't know whether these numbers are typical. And yet you can obtain something. And 10 years ago, Florian Luca and I proved that discriminants are usually large for random curves. And in doing so, we had to revise one of the results of Carter, Granville, and Tucker on square divisors of values of quadratic polynomials and improve it so it would suit our purposes. Okay. So that's more or less what I wanted to say about arithmetic structures. And now I want to look at a very different question concerning the group structure. So we're back to our original question, group structures. But I want to accept a very different point of view. Instead of starting with elliptic curves and ask what happens, I'll start from the other end. I fix a group and ask whether I can realize this group as a group of points on an elliptic curve. So I write my group now in a slightly different way. Instead of ZL cross ZM, I will change my notation a little bit. Now it will be Zn. So what used to be L is now N. But what used to be M, the exponent, is now N times K. So K is an extra divisor over the smallest guy. And typically you expect N to be tiny and K to be huge. But it's only typically. But there are examples with the other way around. For example, K could be 1. Well, and now there are two equations, at least two equations. First of all, you can fix a pair, N and K, and it fixes the group, and ask whether you can represent this group by using all curves which exist in the universe. And in the second equation, you can fix the field and ask only about curves from a particular field. So you have two different equations to address. Certainly you have more flexibility here. But it does make this equation less interesting, of course. Okay. So it's like the inverse problem of Galois theory. We need to recall what we know about N and K and something which we discussed, but because the terminology has changed, let me revise it and put it in the form which is suitable for our purposes now. So what we know, now the number of points will be N times Nk, which gives you N squared K. The number of points is now of this shape. And of course, it's Q plus 1 minus T for some T in the Hasse, in this interval. And the wave pairing tells us that N divides Q minus 1. We have already seen it, but N was L at that time. So, what we know could be summarized on these slides. And you see here, I introduce one more parameter, L. And you can easily check that in this notation, this condition and this condition can be formulated in the shape of this equation. So Q should be represented at N squared K, and this is, of course, the main part. It's the cardinality. And the trace is of this form now, N times L. And L should run up to 2 times square root of K. So it's very easy to reshape these conditions into this form. Now, as you see, the statement says if Q is a prime power, then what's really important to remember that, first of all, these conditions are almost if and only if, but not quite. So if you say it's if and only if, you will be wrong, but not very wrong. And actually, if Q is prime, It's just if and only if. So for prime numbers, not for prime powers, for prime numbers, these conditions are equivalent. So if Q is of this shape, then there is a curve which satisfies this condition. So it's only for primes, I repeat it again. Okay. So let's address our first question, where you just deal with all fields. You don't fix the Q. You're given n and k, and you want to know whether there is a curve somewhere with this group structure. Well, so let's try to count something. And my first set is a set S sub pi, and it's a capital pi. And everywhere throughout my talk, capital pi will refer to just prime powers, including primes, of course. When I use this lowercase pi, it appeals only to primes. So usually sets which are indexed by capital pi are bigger than sets which are indexed by just lowercase pi. Okay, so what are these S pi's? S sub pi is just set of all pairs n and k for which we have a representation. It's exactly the set we want to characterize. So it tells you what groups may appear as groups realized by elliptic curves. And a priori, it could be just Z cross Z, right? Everything could appear. Right? There's no immediate reason to believe that something would not happen. And as with this pi, it's the same thing, but we use only prime numbers. Certainly, it's an interesting case to address what happens if you only consider curves over prime fields. And let me notice that you'll see some results of our calculations. Let me just make an essentially trivial result, that when a pair nk is given, you can test these inclusions in finitely many steps. Because, of course, when nk is fixed, it bounds q, right? Because it's Hathaway bound, because the cardinality is n squared k, so q is not far away from n squared k. So q is fixed, and there are only finitely many curves. Of course, you can do it more efficiently, but at least we know that now there is a finite algorithm to check the inclusion. And, well, a priori, as I said, we can't even rule out the possibility that both the sets are n cross n, namely contain all integer pairs. But when you start computing and actually checking what's going on, you will see that these sets are massive, but the complementary sets are not very sparse either. So this is a table which shows all misses with n and k up to 25. So we have about 600 pairs, and what is this? I think it's 18 pairs which are missed. Yeah, right, out of 600 pairs, more or less, available to us. Okay, so let's do some counting, and I introduce two more parameters, capital N and capital K. So I count pairs with this restriction. So I count the sets in a box, as we usually do. And I want to get some estimates on this. Okay. Now, I kind of can count it in several directions. And one way to try to say something interesting about the sets is to address the following function, or the following set first. We fix a pair n and k, and count the number of primes for which this group, the group you're interested in, is given by some curve over Fp. You can do the same for prime powers, and it would be j sub capital pi. We don't do it because we cannot say anything interesting. Whatever we can say about the sets always appeals to primes. So we just don't know how to study the function which addresses prime powers here. It's not to say that this function is not interesting, we just have not been able to say anything about this. And again, we can count these things. It's almost the same as counting the cardinality of this set, except that now I count this with multiplicities. If instead of summing the cardinalities of the set, I sum only once when the cardinality is positive, it will be the counting function for the previous set S sub pi. Right? Because it counts representations as multiplicities. S just tells you yes or no. Okay, this is the function which we'll discuss. And I want to introduce two more sets. I will remind the definitions later. I just want to show you, give you some spirit of problems we are going to discuss. Two more sets which tell us how much this lemma, I think it was lemma 6, is not an if and only if statement. So let me start with this set. This set is defined just in terms of integers. The definition mentions nothing about elliptic curves. These are just the conditions which lemma 6 imposes on these integers. So this set n sub km has two parameters, k, which is one of the integers, and m, which tells you we work with fields of p to the m elements, but p is not fixed. It's just a type of the fields. And this set counts exactly the number of fields of p to the m elements for a fixed m, for which there is a curve with a given group structure. So the first observation, because I said when we talk only about primes, both statements, lemma 6 is an if and only if statement. This can be rephrased as a statement that n k1 is the same as n tilde k1. There's no difference between these two sets when m is 1. So these purely arithmetic conditions are fully equivalent to the existence of a curve when, again, m is 1, when we work over prime fields. Okay, now we need to characterize the cardinalities and group structures. And this slide, of course, it's very messy. The only purpose of the slide is to show you that there are conditions which fully describe you what cardinalities can appear. Over prime fields, the condition is very easy. Just everything which fits in the Hathaway interval can be realized as a cardinality. Over other fields, there are some exceptional cases which give us some headache. Right? So you see 6 conditions, and they sometimes are painful to handle. And certainly I don't encourage you to look carefully at these conditions. We don't need it now. We recall it when we start using them. And also there is a full characterization of possible group structures, again in terms of some divisibility, p-divisibility conditions. And again, when we work over prime fields, the answer again, everything which is allowed by the Hathaway and the Way pairing can be realized. Over non-prime fields, there are some other exceptional cases you have to keep in mind and take care of. So again, let's not worry about this now. But as I said, for primes, everything is nice and easy. And if your cardinality n is in the proper range, if you have two numbers n1 and n2, used to be L and M before, but now I call them L n1 and n2, with these divisibility conditions, then there is a curve with the structure, with the group structure Zn1 cross Zn2. And again, it's one more reformulation of what we had before. Okay, so if you recall the definition of this set, the set which counts the number of primes which gives you a prescribed group structure, then you will see that for this set, the counting equation has nothing to do with elliptic curves. Essentially, you count the number of primes which can be represented in this form. So beyond this point, you don't have to know anything about elliptic curves. It's just a pure analytic number theory equation. Just count primes in this funny form. And again, this statement, this corollary 10, means that this famous lemma 6, which I already mentioned several times, is an if and only if statement. Okay, So we need to count primes in this form. And please note that the only free parameter here is L. Everything is fixed. Right? N and K are fixed. So this, the major chunk of my prime P is given by this expression, and L runs in this interval. So essentially we talk about primes in the arithmetic progression. So the modulus of the progression N, and L is a free variable. At least it's already something which we know has been studied in analytic number theory. What's really bad here is that the progression doesn't start from the origin. The progression starts from n squared k. Okay, anyway, we are back to analytic number theory, which at least for me it's my comfort zone. At least I know what to try. So we have to count the number of primes in this arithmetic progression. And if we average over n and k, we still work with arithmetic progressions, but now many progressions altogether. So it makes our life easier. And we see that if you use a standard definition of pi of xma as a function which counts primes up to x in a prescribed arithmetic progression, namely in the residue class A mod m, then this quantity can be represented as this sum. We count all n up to capital N and L up to 2 times square root of capital K, because otherwise it runs up to square root of small k, right? But small k itself runs up to capital K. And here we have the difference between two pi functions. Why is this difference? It's exactly because we count primes starting from this point. We don't count them from the beginning of the interval. So simple manipulations, algebraic manipulations, tell you that this is our counting function. So we need to study this difference. The difference of this pi function counting primes in arithmetic progression, which is certainly good news. We express this quantity via some classical functions. The bad news that we need to study these primes in very short progressions. If you look at this expression, you see that this quantity is not that far away from this quantity. Right? We subtract, which means we study primes in a very short interval, in an interval which is close to n squared k. And of course this is bad, and because unconditional results are very weak in this case. But it's not the end of the story. The good thing is that we have to do it on average. We don't have to do it for any n here or any L. Remember, we had a sum of these guys, so we do it on average. And here we have very powerful tools, mostly related to the so-called Bambieri-Vinogradov theorem, which already has been mentioned many times today. Well, but when you try to use it, you see that, well, you became optimistic too soon, because the modulus is n squared. Bambieri-Vinogradov gives you a very good control over these functions when the modulus stays on the middle position here, runs through integers, consecutive integers up to a certain range. Here the modulus runs via squares. Bambieri-Vinogradov in the classical form doesn't tell you much about this situation. And here, when we started working on this, we got exceptionally lucky, because at the same year when we kind of started thinking about this, Byron Zhao, and then in a stronger form, Roger Baker, obtained exactly this version of Bambieri-Vinogradov which we needed, with the modulus running via squares of integers. It was kind of custom made for our applications, even if, of course, the motivation was just to extend Bambieri-Vinogradov to this situation, to this case. Well, let me just explain what Bambieri-Vinogradov tells you exactly. Because of many reasons, instead of counting primes, it's better to count primes with their logarithms. So it's more convenient to define a function psi, which is the function which counts n in arithmetic progression a mod m, and lambda n, where lambda m is a von Mangold function. So what is that function? Slightly abusing the definition, lambda n is 0 if n is not a prime number, and log n when it's prime. And forget about prime powers. It will not affect the result. Right? So for prime powers, it's also defined at log p, but don't worry about this. It changes nothing. Okay. So if you take just sum of all logarithms of primes up to x, it's asymptotic to x. It's a prime number theorem. For pi, it's x over log x. For psi, it's just x. The sum is asymptotic to x. So if you take primes in a prescribed arithmetic progression, the expected value of this function is x, the total number, divided by the number of possible progressions to consider, which is phi of m. Because primes, of course, only fall in progressions a mod m, where a is relatively prime to m. So there are phi of m possibilities for primes. Okay. So in a classical form, the prime number theorem, at least in our present knowledge, if you don't assume the GRH or anything else, will tell you that the actual number minus the expectation doesn't exceed x divided by log x in any constant. So you choose any constant, 100, and you have this inequality, where, of course, the implied constant will depend on c. And the Bambieri-Vinogradov tells you that even if you sum up all these errors over all m up to square root of x, just a little bit less than square root of x. So now I put a lot of error terms together. And if I do it in a naive way, of course I have to put x to the 1/2 on the right-hand side. But Bambieri-Vinogradov tells us that we shouldn't do it. The right-hand side doesn't change. So we estimate all this error term together with the same quality, with the same strength as each individual term. It's a very great result, and it comes from our control over the Siegel zero. Okay, so this is what classical Bambieri-Vinogradov tells us. And Bayer-Zhao obtained an exactly the same result for m squared instead of m. Except, well, here you stop at more or less square root of the length of the interval. Here the modulus is m squared, so if you take this number and kind of consider it in terms of x, m squared would be 43 over 90. It's just a little bit below the square root of x on our new scale, because now we talk about squares. If they had it with 45, it would be exactly the Bambieri-Vinogradov. So the only losses compared to Bambieri-Vinogradov is that they have 43 instead of 45. Otherwise, it would be a precise analog. You run up to the square root of the length of the interval, and you have this asymptotic formula. So it's a very nice, very powerful result. So they work with a very sparse sequence of moduli and have this estimate. Okay. So essentially, when we saw this, we knew that we would be able to handle this equation, but still there is some considerable amount of pain to go through if you really want to get a result, and probably now I don't have time to discuss it. And the main thing is that everything is moving. We have two parameters, n and l, in our sum. We come back here. And everything depends on them in a very ugly way. Your starting point changes, everything is changing. Your progression changes, everything kind of moving with n and l. So we have to do something else on the top of this, but finally you get a result. So the upshot is we were able to deal with this quantity j, with the counting of primes, which represents groups parameterized by n and k, for n and k in this box, in this range of the parameters. Okay, now these sets. These sets are similar to J, except now we don't count the multiplicities of representations. We're just interested in yes or no. Given a pair n and k, we don't care how many times it's represented. We just sum up the characteristic function of the set of primes which give it. And well, we also address this in our paper. And a little bit later, as you see, several authors, including Chantal, obtained a much better result. They extended our previous results on the range and on the quality. So what we know now is that if n runs up to k to the 1/4, then we just have an asymptotic formula. If n is a bit bigger, but still up to square root of k, we know that this set is of positive density. Obviously, the cardinality of the set cannot exceed n times k, right? The set of all pairs. So this low bound tells you that if n is up to square root of k, this set is of positive density. There are at least c times nk pairs. And as I said, if n is smaller, then you just have an asymptotic formula. Almost everything is represented. On the other hand, we can also have an upper bound on this set. And you see that if you take n and k of about the same order of magnitude, this bound is trivial. Because obviously this cardinality doesn't exceed n times k. But here, instead of k, I have k to the 3/2. It looks like the bound is a way weaker than the trivial bound. And it would be if not for this log n. So this bound gives me something meaningful if n is huge compared to k, namely when log n is able to offset my losses in the numerator, which is k to the 1/2. So if k is tiny compared to n, that I'm in business. Well, and this is a very nice nice result. At least I can derive some meaningful statements out of this. For example, we now know that there are infinitely many pairs n and k which are not in the set as sub pi. Why? I think it's around pi, small pi. Why is it so? Well, let's take n to be e to the capital K. Then, of course, I have capital K in the denominator. So the cardinality of this set, when parameters vary in this way, is very small compared to nk. So there are lots of misses. So it gives me some very interesting statements which I don't know how to derive otherwise. In the same way, for any k node, we see that almost all pairs are not in the set. Of course, it's a cheating way to count, right? Because now I favor n compared to k too much. Yet it's a very interesting statement. It says that if you look at this horizontally, that all the lines are almost empty. And recently, Chantal, in collaboration with some other people, extended some of the results to a much more general case of abelian surfaces. I still to look carefully at this paper and understand what actually they're doing there. So I cannot comment on this right now. Okay. Now, we can reverse the equation, and instead of saying that k is kind of small compared to n, you can ask a dual equation and ask what happens when you fix the first component and what happens on these lines. Well, so when a node is fixed, is it true that for almost all cases we have this? So almost all guys are there. And unfortunately, we have no answer to this. So this looks like an easy equation. Nevertheless, we were not able to handle it. Okay. Now, another issue which was of our interest, when I say us, it was Bill Banks, Francesco Papalardi, and I, was to see whether we really had to define two sets. Sets which deal with primes and with prime powers. Do we need prime powers if you want to represent groups? It's quite conceivable that whatever we can represent can be already represented by curves over prime fields. Why not? We have the set of prime powers is negligible. And it turned out that no, primes are very kind of much more frequent than prime powers. Yet they don't give you everything you can extract. So the difference between these sets is reasonably large, actually very large, compared to what one could expect, even when k is 1. K is 1 means that you talk about groups Zn cross Zn. And in this case, there are very mixed structures which you obtain from primes, and you really need to go for prime powers to get them. But this is only for k equals 1. And this explains why this happens. I probably skip this part, but let me mention this question, to which we still don't have an answer. We don't know what happens when k is 2. Maybe in this case, we don't really need prime powers. Maybe the only case when prime powers are important, if you want to represent group structures, is when you deal with Zn cross Zn. We have no feeling, we don't know what to expect for this question. Obviously, we haven't found any structure in this set with k greater than 2. Otherwise, it would not be an open question. Okay. And probably the previous question brings us to a somewhat related question about the sets n. Let me again remind you the definition. N sub km tells us what integers n may appear in these representations. And we are allowed to work on prime in fields of cardinality p to the m, where m is fixed. You can choose any p, but m is fixed. So the type of your finite field is fixed. It's an mth degree extension of a prime field. And n sub km tilde is defined in terms which have nothing to do with elliptic curves, just some conditions on prime powers. So these conditions reflect the Hasse-Weil bound and the divisibility condition coming from the Weil pairing. And we obviously have this, and this is our lemma 6, which was an if statement. And we want to know whether this difference is large, maybe empty. And actually, we know that when m is 1, when we work over prime fields, these sets are the same. And again, it's another formulation of what I said, this lemma 6, the characterization of n, k, and l, is an if and only if statement if you work over prime fields. This means that these sets are the same. Well, now, if m is 2, the situation turned out to be much more complicated. And in fact, in this case, these sets n sub k2 and n sub k2 tilde are the same, except several special values of k, which are listed here. So there are infinitely many values of k when this is not true, when this set is strictly bigger than this one. And in fact, we even know the difference between these sets. So in these two cases, the difference is really negligible. Just one value of n, which is 1. In this case, in the case when k is a square, integer square greater than 1, the difference between these two sets contains at least this, which is related to primes in arithmetic regression. So for these primes, you have you have a curve which you have a pair of so let me say it again. No, not pair. You have a value of n for which satisfies the arithmetic conditions, but for which you cannot find a curve in FPM. So this difference is reasonably large. And the proof uses some property of the Pale equation and some other things. But if you put everything together, you can say that this set is quite small. And actually, you almost know the cardinality of the set, at least when K is not a perfect square. And in this case, you have this upper bound. When K is 1, we even have an explicit expression for this set, which involves a counting function of primes up to t minus 1, if t is a limit up to which you go. And then this quantity is essentially the same as here. But there is something which you have to subtract, because sometimes you overcount primes. And this is a function, it's a counting function of twin primes, which unfortunately we don't know how to control. You can have an upper bound on this, but we don't have an asymptotic formula for this. So you can play some other games with these quantities, but when you go to m equals 3, everything stops. So you don't have any non-trivial statement which addresses the issue m equals 3. So you lose your control over the situation instantly, even when k is 1. So we don't know what to say about n, 1, 3. We don't know anything about this set. Okay, now let's talk a little bit about some numeric results and some heuristic results. And you will see that they slightly deviate. So we decided to compute and see what happens when you try to study the things numerically. So this is a counting function of the number of missed pairs n and k, which don't lead to a group structure on an elliptic curve, where both n and k are bounded by d. So we work in a square of side length d. And this is a function which shows how it goes. I will talk about this a little later. And another thing to count is just to put k and n in a rectangle besides k and n, and then you have the 2D picture. Instead of putting everything together and counting the total number of pairs, now I'll limit each of them, right? And now it's a function of two variables. And this is the plot which you obtain. Okay, yeah, I will comment on this a little later. For now, I just show you a picture without any comments. So, of course, we try to explain and to understand what we.
Can you just go back to this?
Yeah. This
What's the number of missed?
Yeah, this is the number of missed pairs. So over everything, something which you cannot represent using whatever curves you can get. P is whatever, or your choice. I give you n and k, you have to give me a field and a curve. And this is exactly when you cannot do it.
It doesn't have to be a prime field?
Anything.
Okay. Any finite field?
Any finite field. Well, yeah, it's a finite. If you can do it.
I see, so their n is on one axis. Okay.
Yeah, so it's kind of a very strange, regular but strange behavior. And we try to explain it somehow. So we try to come up with some heuristics. And actually, what's really strange was that along every line, n fixed to n node, it becomes kind of a straight line very soon. So it behaves strangely here, but then it kind of starts growing linearly. So we try to explain what's actually going on here. Okay, so let's develop some heuristic and then try to compare it with numerical results. So a pair n and k contributes to this if this is not a prime power for this L, right? And in some other small exceptional cases. It's more or less applying lemma 6 as an if and only if statement, because we know it's almost correct. So if this is a prime power, then we have a curve. It is kind of bending our statement a little bit, but not in a very bad way. Okay. So what's the standard heuristic for this guy to be a prime power? You can forget about prime powers. They're not very common. So let's talk only about primes. And all asymptotic formulas tell us that it's the right point of view. Prime powers do not contribute to count. They give you some exceptional cases, interesting exceptional cases, but not to just a case of statistical count. Okay, so what's the density of primes? Well, the probability that n is a prime number is 1 over log n. So we take the size of the number which we want to see prime and put its logarithm in here. And also we should remember that we seek for prime powers in an arithmetic progression 1 mod n. Right? This number, minus 1, is divisible by n. So there is some embedded arithmetic structure. So instead of writing 1 over log this guy, we need some correction. Right? And this correction works in our favor, because it's not divisible by n. It's already good to know. Right? It increases the chances to be prime. And the correction factor is exactly this, n over phi of n, which pushes it a bit up. Okay? Now we have many values of n and k, and each of them contributes to the probability of kind of hitting a curve. So this doesn't happen, at least it looked to us. With this probability, we take 1 and subtract the probability not to be a prime power, and we multiply, right? Because we consider these events as independent. Again, don't ask me for proofs. Of course, I don't have any, but it looks like it's a reasonable heuristics. And we obtain this function theta of nk, which is a probability that n and k contributes to this function. Okay. Now we sum it up, and and we have this function b, which would give us a prediction for f. This is a heuristic prediction. Probably we can study this function analytically. We didn't do it. We just know that there are two extreme cases where it's asymptotic to 1 and when it's very small. So only the gray area between around log n squared is where you have to do something. Anyway, we just computed this function numerically. Right? We just forgot about elliptic curves and started computing this function just from explicit formulas and try to compare this with f. And this is what we got when we took the ratio. And it looks like, you see, it becomes kind of flat. And when we looked at this, we said, oh yes, very good. Right? We expect it to be 1. But when we look more carefully, it becomes flat not at 1, it becomes flat at 0.7. And we have no explanation whatsoever to this. So what do we miss in our analysis? We have no idea. Obviously, our analysis is not completely out of place, right? Because the functions are clearly related, right? The thing becomes stable. But why it stabilizes at 0.7 instead of 1, we have no clue. And if
Can you just go back a few slides where you had the case where
this?
one more. So doesn't if L has common factors with K, that's going to increase the probability that you're a prime factor. So
Yes. But it's, well, you take this number as given, right? Maybe you're right. Maybe there should be some kind of analysis taking this into account. We don't know. Maybe this will affect it. We just don't know any better model. Probably. Well, obviously we are missing something. Right? There's no doubt that we are missing something here. And it would be nice to understand what exactly is missing in our analysis. Okay, now I have a few more minutes to talk about a different situation when the field is fixed. So now we have Q and it's set in concrete. We don't change the field and we have the same equation. What can we get out of curves from a given field? And here I count the number of isomorphism classes of elliptic curves such that the group of points has a prescribed structure, Zm cross Zn. I apologize that again I changed the notation, but I decided that changing and synchronizing, because things came from different slides, from different papers, would generate more errors. So unfortunately I have to change my notation to M and N. Okay, so we know how to characterize M and N lemma 8, which is mentioned here. It's exactly the ugly lemma which tells you what group structures may appear provided some arithmetic conditions are satisfied. So when we need to check something, we have to recall this lemma and check whether this happens or not. And generally we compute this quantity via some sums of class numbers, and you have some strange formulas here which involve square divisors and so on and so forth, which again I prefer not to discuss here. If somebody is interested, my slides will be available. You can look into details of this. And I just tell you that you can get some asymptotic formulas for this. Well, now, the function which would correspond to what we did before would be the function f of q, which just tells you the number of distinct structures which you can get from q. And this function behaves in a reasonably regular way. It's a sum of the divisor function over square divisors of this expression. S of t is divided as the largest integer which satisfies this condition. So again, there's a purely arithmetic characterization of S of t, and together with this formula plus some tiny error term of size O1 allows you to get some analytic tools into this, bring in some analytic tools, and this is what we managed to prove. These asymptotic formulas work for different types of Q. So first of all, if Q runs to infinity, this function could be as big as this constant times square root of Q1 minus 1 over P. It's lim sup. There's no limit here. And probably limit doesn't exist here. In fact, probably doesn't exist. But if Q runs via odd prime powers, then the lower limit is 5. So this means that there's no limit at all, right? Because the lim sup and lim inf deviate.
Can I ask a question? So is P fixed?
No. Q runs to all prime powers.
Oh,
P is not fixed.
All prime powers.
All prime powers, but when you scale, of course, you take P from Q.
I see, so you take all prime, you don't.
You take Q is an okay. What it says? There are infinitely prime powers Q, such that if you divide f of Q by square root of Q, y minus 1 over P, where P comes from Q, then you get this. So a purely puristic point of view would be to say P sub Q, because P is a function of Q here. It's a prime which goes into Q. So upper and lower limits are like this. So this is about 10, 20, so it's about 7 and 5, right? Numerically, something like this. But if Q runs over even powers, namely it's 2 to the k, then the lower limit is 2. And you can also estimate this function on average, which gives you something. Okay. So this is
You take all prime powers up to X.
here we take, yes, all prime powers up to, well, we call it capital Q, and this is what you expect. So you see, it's square root of Q, right, which obviously dominates, something which you would expect. And on average, it tells you, yes, it is. With some funny constant which depends on the series, which is multiplicative. There is a Dirichlet product here. You probably can even get a better bound on the error term than little O1. Okay. Having done this, we decided to study what's the most popular structure. Namely, this function g of q mn tells you the number of curves with a prescribed group structure which is controlled by m and n. At the moment, it's not even necessary to remember how m and n control the structure. Something which defines the structure uniquely. So what's the largest hit here? And the standard bounds on the class number tell you that g of p should behave plus p to the 1/2 plus little o of 1. Unfortunately, in the exponent. So it's not an asymptotic formula. It's a asymptotic formula on the logarithmic scale. But it makes it natural to study this function if you scale it with square root of p. We know it's there, so it's only this little o of 1 which is interesting to study. So we experimented with primes. We had no idea how to do this analytically. And what we discovered that, first of all, it's more natural to scale this quantity, not by the square root of p, by log p. So log p is hidden somewhere here. We don't know how and why. And in this case, this quantity stabilizes somewhere in here, in this strip between 0,1 and 0,2. So of course, when we know what happens numerically, it makes sense to try to come back to this equation and try to see what's exactly this little o1 looks like. So this is what our computations show. This is how this quantity behaves. When you scale it again, not by square root of p, but square root of p log p. So maybe this is the expectation. Yeah. And what was interesting to discover that cyclic groups usually are the most common structures, which means that M is 1. So G of Q and 1 almost always wins. But not always. Almost always, but there are some exceptions when M equals 2 was the winner. And I think a couple of times they just break even. We never observed anything coming from M equals 3. So this, if it's not cyclic, right, the non-cyclic component is tiny. Never exceeded 3, but maybe we haven't computed far enough. So we have no idea what is going to be on this. Okay, now, it's also natural to compare G sub p with I of p, which is the largest number of curves in isomorphism class. Of course, if curves are isomorphic, their groups are the same, but not the other way around. Right? Curves could be completely different. They have to have the same number of points. They have to be isogenous. But they're not necessarily isomorphic. They can lead to the same group. And we decided to compare whether this is really the case. So this is another thing which you cannot explain. So we took these ratios between G and I. And this plot shows that there are some horizontal lines which you have no idea how to explain. Of course, there is one horizontal line which you cannot see here because sorry, no, never mind. Okay. So you see some horizontal lines, and you see there's nothing here. And that was actually why I was suspicious of your talk on the first slide when I asked you what's about white area. Because here you also see a completely white area, but it's not empty. You just cannot see it here. There are some points, namely points which are listed here, which live in this region, which makes it completely mysterious. So it's not typical, but it's not completely forbidden. It's a very rare event. We have no idea why. We have no idea how to explain these horizontal lines. We have no idea how to explain why this area is not completely deserved, but very sparsely populated. We don't know whether it's going to continue. So there are lots of mysteries here, and certainly I would prefer to know more about this. This summary of the equations which kind of address this issue. Even some numerical study would be appreciated, but of course if you can get some theoretic insight into this, that would be of great value, I think, in our understanding what happens with elliptic curves. Okay, I think I've done.